Hi, this is Mrs. Young, and this is our second lesson in our circle units. Today, we're going to talk about arcs and chords in a circle. There's quite a few definitions and theorems in today's lesson. We're going to start with a bell ringer, which connects back to a theorem from yesterday's lesson, the first lesson in circles, where the tangent lines meeting at an external point are going to be congruent. So using that theorem, you can go ahead and solve these two bell ringer problems. So pause the video, take your time, and solve these two problems. So the one on the left, number one, when I set those two expressions equal to one another and solve it algebraically, I get x is 3. But I'm not done because then I know that I need to solve for EF. So I take 3 and plug it in for X, and I got EF is 7.8. A way that you could actually maybe double check your answer too is you could take 3 and plug it in for X in the other expression, and you should also get 7.8 because those two segments, EF and EG, are congruent or the same measure. So just a way to kind of double check your answer. The second one, number 2, is a little bit harder. When I set the two expressions equal to each other, the first thing I would do is get rid of my fraction. So I'm going to multiply both sides by 2. But then I notice that I have something squared. So think back to your algebra skills there. I'm going to have to do some factoring. So I move or subtract the 10x over to the same side as the x squared. You always want your squared variable to be positive. So don't move x squared to the left side. Keep it positive on the right side and subtract the 10x over. Then we're going to factor out a common factor of x. And then you're using something called the zero product property from algebra. If something times something is 0, then one of those two must be equal to 0. So either x is equal to 0 or x minus 10 is equal to 0. Well, we know that x cannot equal 0 because if I plug that in, I would get the length of a side being 0. So that cannot happen. So we cancel that out. We eliminate that option. Using x is equal to 10, I can plug that in to solve for EF. 10 squared is 100. 100 divided by 2 is 50. Again, a way to double check this, I could take 10 and plug it in on the other side. 5 times 10 is also 50, so the same value. So that is true. So EF is 50 feet. Okay, jumping in or diving into our lesson for today, we're going to start with some terminology. Central angle, I think we have talked about central angles before. It's an angle whose vertex is the center of a circle. So here's the center of my circle, circle C, and this angle ACB is a central angle. Arc, another vocab word, an arc is an unbroken part of a circle consisting of two endpoints and all the points on the circle in between them. We use, instead of a straight line, we use like a kind of a curved or arced line above that. So that's arc AB. I am pretty sure arc is in your vocab packet. I don't know if you still have your vocab packet or where that might be, but you could always write these down if you'd like to. So maybe pause the video and copy down the vocab if you feel you need that. Now going a little bit further into our concept of arcs, there are special types of arcs. So there's something called a minor arc. It's an arc whose endpoints are on or in the interior of a central angle. So AB, arc AB, is a minor arc. The measure of a minor arc is equal to the measure of its central angle that it's across from. So if this central angle ACB, let's say that that central angle was 40 degrees, then we would know that the arc across from that, arc AB, is also 40 degrees. It's an important property about arcs. A major arc is an arc whose endpoints are on or in the exterior of a central angle. Again, this is my central angle. So arc ADB is called a major arc. The major arc is equal to 360 minus the central angle. That should make sense to you because we know all the way around a circle is 360, right? So if I take out the 40, that means that this arc ADB is going to be 320. A semicircle is a special type of arc whose endpoints are on the diameter, and we know that the measure of that would be half a circle, so that would be 180. Minor arcs are named by 2 points, AB. Major arcs and semicircles must be named by 3 points. right? So we couldn't call this arc AB because we would think you're talking about the smaller one. So you have to use 3 points ADB. The major arc is always the bigger arc and the minor arc is the smaller arc. And also in semicircles, if you, oh gosh, I didn't label this, but let's say that this was X and Z, right? But I wouldn't know if you're talking about the left side or the right side, and that's why you have to have a third point in there so we know which side or which semicircle you're referring to. So you have to have 3 points for a major arc or a semicircle. A lot of terminology here. So pause this and go ahead and copy that down. So here's just a really quick application problem. The circle graph shows the types of grass planted in the yards of one neighborhood. Find the measure of arc KLF. So I'm going to do this one with you. Arc K, let's see where it is, KLF. Again, they're using the 3 letters, so they're referring to that major arc. It's 65% of the whole circle. Well, you know a whole circle is 360. So if I take 65% times 360, or maybe you would in your calculator punch in 0.65 times 360, then you know that the measure of that major arc would be 234 degrees. So again, definitely needing my calculator for this, right? But it's that portion of the big circle. The whole circle is 365. Centipede grass, which is arc KLF, would be 234 degrees. Just like if I asked you to find the measure of arc KH, right? Then you would take 7% times 360 to get the measure of that arc. Again, the arc is the same measure as the central angle that it's across from. So just a quick little practice problem there. Moving on, a few more terms here. An adjacent arc, or sorry, adjacent arcs, plural, are arcs of the same circle that intersect at exactly 1 point. So they meet or touch at that 1 point. So we can see that arc AB and arc BC are adjacent at that 1 point, at point B. So those are considered adjacent arcs. We have a postulate called the arc addition postulate, very similar to the segment addition postulate or the angle addition postulate. It just says that the measure of arc AB plus the measure of arc BC would give us the measure of arc AC. So as an example, if I said arc AB was 30 degrees and arc BC was 40 degrees, then we would say AC is 70 degrees. So you just add those 2 pieces together. So then just like the segment addition or angle addition postulates that we've seen before. So pause the video and go ahead and copy down this definition and postulate. So a quick example here, it says find the measure of arc BD. So thinking of all the things that we've talked about so far, here is BD. How could I find the measure of that? Well, I know that BE is a diameter. That's 180, right? So if I take 180 minus 52, 180 minus 52, I should come up with 128. So that means that not only is the central angle here, right, this angle is 128, but it also means the arc across from it is also 128. So just a quick little application problem. Let me just show you another one. Here it says find the measure of arc JKL. So here's JKL. We're talking about that arc. Again, I can see that JM is a diameter. This arc is 40. So again, 180 minus 40 is 140. So my guess is that this angle is 140. So then the arc across from it is also 140. Let's check and see if I'm right. Yes. Okay, then arc LJN. Let's see, LJN. Whew, that's a huge arc, right? That's a major arc. But I can see over here that this is 40 and this is 25. So those two add up to 65. So I could just take 360 minus 65 and get 295 degrees. So again, I'm looking for LJN, which is this major arc. If this central angle is 65, then I have 295 left for the other side. So I'm going to guess, hopefully I got 295 right. Yes. Okay, so moving on, we do have a little bit more to go here. More definitions. Congruent arcs, two or more arcs that have the same measure. So we know what congruent means. It means they're the same measure. So two arcs like ST and UV are congruent. Notice that they're across from the same size central angle, right? So if these central angles are the same, then those arcs are going to be the same. And congruent just means they're the same measure. So we have three little quick theorems here that we're going to write down. I tried to abbreviate these as much as possible. So go ahead and pause the video and copy this down with a picture, and then I'll come back and talk about it. So go ahead, pause it and copy it down. Okay, so these three theorems are all interconnected or related. In a circle or congruent circles, congruent central angles have congruent chords. So if these central angles, as an example, if that central angle EAD was congruent to CAB, then we know that the chords across from them are congruent. If we have congruent chords, then the arcs across from them are congruent. So if chord ED was congruent to arc CB, sorry, chord CB, then we know that the arcs ED and CB are also congruent. If our arcs are congruent, then we know that our central angles must also be congruent. So it's kind of a cycle going between the three things. If the central angles are congruent, then we know the arcs and the chords are, and vice versa. So you just need one relationship there to connect to the other pieces. Notice that I said in a circle, which I did here, but it's also true in any congruent circles. So if they give you congruent circles, you can still apply these same three theorems. I'm going to go ahead and go over just a couple of quick practice problems with you. TV is congruent to WS, find WS. So obviously, if TV is congruent to WS, then we know the arcs across from them are congruent. So we know that 9n minus 11 is equal to 7n plus 11. So this is a really simple algebra problem. I'm going to add the 11 over. Let's add 22. So I'm going to get n is equal to 11. But notice that it says to find the measure of arc WS. So I'm going to plug it in here. 7 times 11 plus 11, so 77 plus 11. I'm hoping that it's 88 degrees. We'll see. Let's see if I got the right answer. Yes. So just a simple algebra problem using that theorem. Let me show you another example. The difference here is that instead of having one circle, I have two congruent circles. So again, if they give you congruent circles, we know we can apply these same theorems. So notice that CD is congruent to EF, which means the arcs across from them are also congruent. So we can say 25y is equal to 30y minus 20. Subtract the 25y over, add the 20 over, and we get y is equal to 4. But again, notice that we want to find the measure of arc CD. So we can take the 4 and plug it in. 25 times 4 is 100. So it's 100 degrees. Again, a way to double check these, just like I was saying in my bell ringer, you could take that value of 4 and plug it in here. 30 times 4 is 120, and 120 minus 20 is 100. You should get the same value on either side. So just a quick way that you can double check some of your answers. I do have, finally, we're getting near the end, 2 more theorems. So these last 2 theorems, in a circle, if a radius or diameter is perpendicular to a chord, then it bisects the chord and its arc. My second theorem, in a circle, the perpendicular bisector of a chord is a radius or diameter. Pause the video and go ahead and copy down these 2 last final theorems. So again, just recapping these 2 theorems, if a radius is perpendicular to a chord, so if this radius right here is perpendicular to this chord, then it bisects the chord, right? It's cutting it into 2 congruent pieces, and it also bisects the arc as well. If in a circle, the perpendicular bisector of a chord is a radius. So the second one is really just the reverse or flip of the other. And again, notice in my picture I have the radius, but this would also be true if it were a diameter. Same application. So let's look at a really quick sample problem here together. It says find NP. So I can clearly see that RM is a radius, and they're telling me that this piece is 8, and they're telling me that this other piece over here is 9, but RM in total clearly is my radius. I'm trying to solve for NP. This is a challenging problem. Here's my thought or suggestion. I don't know if you thought of this, but what if I drew in an additional line going from R to N? That's also a radius. I know from this piece right here that my radius is 8 plus 9, so it's 17. So I know that side, that distance, that radius is 17. Notice also that you have a right triangle here, right? You've created a right triangle. We know it's a right triangle. We know this is perpendicular, right? So if one leg is 8 and the hypotenuse is 17, can I solve for the missing leg of that right triangle? Sure. 8 squared plus, let's call that b. b squared is equal to 17 squared. Go ahead and pause the video and solve that. So when you solve this, you should get b is equal to 15. So if this length or distance is 15, what's the measure of segment NP? Again, we know that this has been, because it's a radius and it's perpendicular, we know that it's bisecting this. So if this piece is 15, we know this other side is also 15. So that total length or distance of NP is going to equal 30. Nice. I could do more practice problems, but I feel like my video is probably long enough. There was a lot of theorems and vocab in this section. So your homework for tonight, again, you can always check your stamp sheet. It's somewhere in Google Classroom, but our homework for tonight is pages 12 through 13. You're doing numbers 19 through 35. Also, all of these theorems and vocabulary that I went through today are also in the packet. So if you want to refer back or look back at that packet, they're on pages 8, 9, and 11. So if you need to refer back to any of that to help you remember some of this stuff as well, you can. So again, there's your homework. Again, make sure that you take a picture and submit your homework to me tonight or before the end of the day. Thanks, guys. Bye.